Hello students, in today's lecture we are going to learn about oscillations, NCERT section 13.8 and example 13.8. This is our disclaimer. Learning objective. After this lecture you will be able to understand a simple pendulum, formula for angular frequency and time period for simple pendulum. This is the index for today's lecture. So first 13.8, the simple pendulum. Then we will solve an example 13.8. Let's start by thinking about periodic motion. Periodic motion means any movement that repeats itself at regular intervals, like pendulum swinging back and forth or the hands of a clock moving around. For example, let's look at a familiar example. A child swinging on a swing. Look at figure. Child swinging on a swing. So, swings moves back and forth in a regular pattern from A to B, B to C, then again repeats C to B, B to A. Alright. As you see here, swing, think about how you might measure the time it takes for the swing to go from the on extreme end back to the same point. This time is what we call the time period. Alright. The figure here helps us visualize the type of motion. But what if you don't have a clock? Can you still measure the time period of this swing? Yes or no? So, here we are discussing observation made by Galileo. Galileo observed a chandelier in a church and noticed a chandelier hanging from the ceiling. Imagine this chandelier as shown in the picture. It's suspended and free to move. So Galileo showed that when the chandelier was disturbed, it started swaying back and forth. This back and forth movement is what we call oscillation. So Galileo realized that this motion was periodic, meaning it repeated at regular intervals. He measured the time it took for one complete swing, called the time period, using his own pulse as a timer. Galileo concluded that the chandelier was acting like a pendulum. He discovered that the time period of a pendulum swing does not depend on how far it swings or its amplitude, as long as swings are small. Alright, let's start by looking at the simple pendulum. So now let's focus on what exactly a simple pendulum is. It's made up of a small bob with mass m. Alright, attached to a string of length capital L that does not stretch and has no mass of its own. The diagram 13.17 shows this setup clearly. Alright, so remember, M is measured in kilograms and L in meters. The other end of this string is fixed to a rigid support. So pendulum can only swing in a single plane. When we pull the bob to one side and let it go, it oscillates back and forth around the vertical line. Around the vertical line, it moves back and forth. Alright. So this motion happens because the pendulum is disturbed from its resting or equilibrium position. So figure 13.17a shows this system. We will use this figure to understand the forces and motion involved. So figure 13.17b acts like a free body diagram for the pendulum. It shows all the forces acting on the bob, the tension in the string and the force of gravity. The radial force, which is T minus m times g cos theta, points towards the center and provides the centripetal force. The tangential force m times g times sin theta is what actually causes the pendulum to swing back towards its mean position. Alright. So let's look at the force analysis of a simple pendulum. So now imagine the pendulum has been disturbed and is swinging. At any instant, the string makes an angle which we call theta. Alright, with the vertical direction. Theta is just a way to measure how far the pendulum has moved from its resting or mean position. Alright. So when the pendulum bob passes through its mean position, theta is 0. That means the string is perfectly vertical. There are only two forces acting on the bob, the tension T along the string and the vertical force due to gravity, that is mg. So when we resolving the forces, force of gravity into two components, the first component mg cos theta acts along the direction of the string, while the second component mg sin theta acts perpendicular to string. Here we are continue understanding simple pendulum with figure 13.17. So focus on the path of the bob. Its motion traces a circle with radius capital L, where capital L is the length of the pendulum string measured in meters. The center of this circle is the support point. So in circular motion, radial acceleration points towards the center of the circle and is given by omega squared times L, where omega is the angular velocity in radians per second and capital L is the length in meters. But that's not the whole story. The bob also has tangential acceleration. This happens because its speed along the arc is not constant. It speeds up and slows down as it swings. Tangential acceleration acts along the direction of motion. So the radial acceleration is caused by the net radial force, which is tension in the string minus mg cos theta, and the tangential acceleration comes from mg time mg into sin theta. Now here our motive is to find the time period of this periodic motion of pendulum for small oscillation. The time period depends on how the forces and torques act on the pendulum as it swings. So to do this, we will use torque, which is a measure of how much a force causes an object to rotate around a point or axis. So the formula for torque is given by tau equal to R cross F. Alright. Here R is the position vector, F is the force. So it's often easier to calculate torque about the support point because the force acting along the string, called the radial force, does not create any torque. Now, torque due to radial force is 0. Therefore, torque about the support is entirely provided by the tangential component of the force. The tangential force is the part of gravity that acts perpendicular to the rod or string, trying to swing the mass back towards its lowest point. So using the definition of torque, we know that torque equals the distance from the pivot R times the perpendicular component of the force, F perpendicular. So torque is equal to R into F perpendicular for a pendulum. R is the length of the string and F perpendicular is the tangential component of gravity. So here is the expression for the torque, tau equal to minus L mg sin theta. So this torque is called the restoring torque because it always acts to reduce the angular displacement and bring the pendulum back to its lowest point. Here negative sign tells us the direction of the torque is opposite to the displacement. Alright. So tau equal to minus L mg sin theta. So connect this to Newton's law of rotational motion. This law says that torque tau is equal to the moment of inertia into alpha, angular acceleration. So here I want to clarify this the terms. The moment of inertia I depends on how the mass is distributed relative to the axis of rotation. Alright, and its unit is kilogram meter squared. Whereas angular acceleration alpha is measured in radians per second. So just like mass resists changes in linear motion, moment of inertia resists changes in rotational motion. Alright. So from equation 13.19 and 13.20, I alpha is equal to minus mg sin theta L. So alpha equal to minus mg L divided by I sin theta. Alright. So let's start by looking at angular acceleration in a simple pendulum. The formula I is equal to alpha equal to minus mgl sin theta divided by I. So if the angle theta is small, which is often the case for pendulums swinging with a small amplitude, we can make an important approximation. So sin theta can be expressed as sin theta equal to theta minus theta cube divided by 3 factorial plus theta raised to the power 5 divided by 5 factorial plus minus and so on. So it's important to remember that theta must be in radians. Validity of small angle approximation. So now let's look at table 13.1, which shows how the sign of an angle written as sin theta changes as the angle theta increases. Alright. So here is the table. For each angle, 0 degree, 5 degree, 10 degree, 15 degree and 20 degree. Alright. The value in degrees equivalent in radians. So it will be in radians, it will be 0 degree, in radians it will be 0 radians, and 5 degree means 0.087 radians. Similarly 10 degree 0.174 radians, and 15 degree 0.262 radians, 20 degree 0.349 radians, and their value sin theta. For sin 0 it will be 0, and sin 5 it will be 0.087. All right, and similarly for 10 degree, 15 degree and 20 degree. From this table, notice that even when theta is as large as 20 degrees, the value of sin theta is still very close to the value of theta in radians. This shows us that for small angles, sin theta and theta in radians are nearly the same. So the key takeaway is that when theta is small, we can approximate sin theta by just using theta itself. Alright. So sin theta is approximately equal to theta. So from equation 13.22, we have alpha equal to minus mgl divided by I sin theta, and can written as alpha equal to minus mgl theta divided by I. So here we use approximation. We replace sin theta with theta. So the equation becomes this one. This is a much simpler form and is labeled as a equation 13.24. So this is very important. This is the relation for angular acceleration in case of simple pendulum for small oscillations. It's important to remember that this relationship only holds for small angles, typically less than about 10 degrees. Derivation of time period formula. So let's start by looking at the expression for acceleration in simple harmonic motion or SHM. The equation A equal to minus omega square into x. Alright. So it tells us that the acceleration is always directed opposite to the displacement, and its size depends on both omega squared and how far the object is from the center. So from equation 13.24, that is alpha equal to minus mgl theta divided by I, equation 13.24 is mathematically identical to equation 13.11 except that the variable is angular displacement. So for small values of theta, the motion of the pendulum bob is simple harmonic motion. This is only true for small angles. By comparing these two equations, we can find the angular frequency omega for the pendulum. So omega square equal to mgl divided by I. This means that if you increase the mass, gravity or length, omega squared increases. But if the moment of inertia increases, omega squared decreases. Alright. So taking the square root, we get omega equal to under root mgl divided by I. This is the final formula for the angular frequency of a physical pendulum. So we have omega equal to under root mgl divided by I. So using t equal to 2 pi divided by omega, time period of this bob executing simple harmonic motion will be t equal to 2 pi into under root I divided by mgl. Alright. This tells us that the time period depends on the moment of inertia, the mass, gravity and the distance L. This formula is very useful for predicting and understanding oscillatory motion in physical systems. So, uh, let's start by looking at the moment of inertia for a simple pendulum. Since the string is massless, the moment of inertia, which we call I, is just m times L squared, where m is the mass of the bob in kilograms and L is the length of the string in the meters. So the figure here, 13.17a, the mass is concentrated at the end of the string. So all the mass is at a distance L from the pivot. So expression for angular frequency omega is equal to under root mgl divided by I becomes omega equal to under root mgl divided by ml square. Angular frequency and time period for simple pendulum. So we have omega equal to under root mgl divided by ml square. So solving this, you will get omega equal to under root g by l. This is the simplified formula for angular frequency in the case of a simple pendulum. So next, let's see how we get the formula for the time period. We substitute the value of the moment of inertia I equal to ml square in the expression of time period t equal to 2 pi under root I divided by mgl. So after substituting, we get t equal to 2 pi under root mgl square divided by mgl. So solving this, you will get t equal to 2 pi under root l by g. So this is the simplified formula for time period in case of simple pendulum. Remember, both angular frequency and the time period depend only on the length of the pendulum and the acceleration due to gravity, not on mass. Conclusion from time period formula. So here is the formula for the time period t equal to 2 pi under root L by g. So first, independence from mass. Alright. So this means the time period is completely independent of mass, whether you use a heavy metal ball or a light wooden one. The time for each swing stays the same. Next, let's talk about the amplitude. So for small angles, the period does not depend on how far you pull the pendulum back. So if you start with a small swing or a slightly bigger one, the time for each swing remains almost the same. Now look at the length L. So the period increases as the square root of the length. So if you make the pendulum 4 times longer, the period doubles. And then dependency on gravity. So if gravity is stronger, the period gets shorter, meaning the pendulum swings faster. Alright. Example 13.8. What is the length of a simple pendulum which takes seconds? Let's see the solution. First, let's clarify what ticks seconds means. The Paris refers to a pendulum that marks each second with a swing. A pendulum that ticks seconds completes one full oscillation in 2 seconds. That means it takes 1 second to swing in one direction and another second to return. So the period t, which is time for one complete oscillation, is 2 seconds. So given this, we can write period 2 seconds. Acceleration due to gravity g equal to 9.8 meter per second square. time period of a simple pendulum t equal to 2 pi under root L by g, and solving for length t square equal to 4 pi square L by g. Alright. So solving for length t square equal to 4 pi square L by g. So L equal to gt square divided by 4 pi square. Putting the value g equal to 9.8 meter per second square and time period t equal to 2 seconds, L is equal to 9.8 into 2 square divided by 4 pi square. So L equal to 39.2 divided by 39.48 is equal to 0.993 meter. So L is approximately 1.0 meter. Hence, length of a second's pendulum is approximately 1 meter. Let's see one more example. Calculate the time period and angular frequency of a simple pendulum having string length of 20 meter. Let's see the solution. Length of this string L equal to 20 meter. So now let's focus on finding the angular frequency. For a simple pendulum, the angular frequency which we write as omega is given by the formula omega equal to under root g by L. Putting the values of g, that is equal to 9.8 meter per second square, and length of this string L equal to 20 meter in the above equation, omega equal to under root 9.8 divided by 20. Solving this, you will be get under root 0.49. So omega equal to 0.7 radian per second. Hence, the angular frequency of given pendulum will be 0.7 radian per second. Alright. Now, calculation of time period. The time period for simple pendulum is given by t equal to 2 pi under root L by g. So, substitute the given values into the formula, we will get the value of t. So, it will be t equal to 2 pi under root 20 divided by 9.8. So, t equal to 2 pi into under root 2.0408. So, t approximately 2 pi into 1.42856. So, t is approximately equal to 8.97 second. Hence, time period of given simple pendulum will be 8.97 second. Alright. Summary. Simple pendulum. It is a system consisting of a point mass suspended by a massless inextensible string from a fixed support. Angular acceleration in case of simple pendulum is given by the relation alpha equal to minus mgl sin theta divided by I. For small angles, sin theta is approximately equal to theta. For small oscillation, angular acceleration is given by alpha is approximately equal to minus mgl theta divided by I. So this gives angular frequency as omega equal to under root g by L, and time period as t equal to 2 pi under root L by g. Seconds pendulum. So this is a special case where the pendulum takes exactly 2 seconds to complete a full swing, or 1 second for half swing. It's often used as a standard for measuring time. Practice questions. First, calculate the time period of a simple pendulum having string length of 10 meter. Calculate the angular frequency of a simple pendulum having string length of 5 meter. And last, calculate the moment of inertia of a simple pendulum having bob of mass 2 kg and length of 1 meter. Alright. Thank you for your attention. I hope this lesson was helpful.